Introduction, Probability, and Counting. When we talk about probability, what we're talking about is the likelihood of something will happen. There are infinite possibilities, but the probability of something to happen can be defined by finite amounts, with a total amount being 100%. Some of the concepts I want to talk about here are these basic definitions we'll be using today. Probability experiment, this is where we get results from doing a probability test, whether it be flipping a coin, rolling a die, or determining who's going to vote for someone, or what kind of poll, what kind of soda someone likes. The outcome, that's the results of these probability experiments. The sample space, this is all the possible outcomes. For example, there are two outcomes when you flip a coin, a heads or a tails. We roll a die, there are 6 outcomes, a 1, a 2, a 3, a 4, a 5, or a 6. And then the event is that subset of each one of those outcomes. We start with a tree diagram here, and I got a simple one here, basically, of blood types. All individuals have one of 4 blood types, A, B, or O. And then furthermore, they can be Rh positive or Rh negative. That gives us 8 possibilities of blood types. These are all the possible outcomes. Now, a simple event usually means there's only a single outcome. If I flip a coin, I can only have a heads or a tails. Even if it's two different components of it, such as flipping a head followed by rolling a die, I can only get one simple outcome. I could flip a coin and get a head and followed by a 1 on a die, flip a head followed by 2, or flip a head followed by 3, and so on and so forth. Same with tails. But we only have a single outcome. Now we can have multiple outcomes, which is not simple events. We could look example at a coin toss and an even die. What I mean by that, you could get heads, and that's only one of 2. But an even die would mean when I roll my die, I get a 2 or a 4 or a 6. Or it could be an odd die, which is a 1 or a 3 or a 5. That's not a simple event. Now, I want to teach you the fundamental counting principles, a very simple concept, and you can see why we use it, because looking at the number of events can get complicated very quickly. Let's suppose someone had a choice of a type of car they'd want based on the make of the car, the size, and the color. And I've only got 3 makes here, I've got 2 sizes, and I've got 4 colors. But even these combinations can get pretty big pretty fast. I could develop tree diagrams. I could start with the make, which is a Ford, and then the size of the car, compact or midsize, and then the 4 different colors for each compact, or the same 4 different colors for midsize. I do the same thing with General Motors for the make, and then compact or midsize, and then the colors falling under each. Or the Honda with the compact or midsize and the 4 colors for each component. When I count all my possible solutions in total, there are 24 variations. You can see the 4 for compact for Ford, 4 for midsize for Ford, 4 for compact for General Motors, 4 for midsize for General Motors, 4 for compact for Honda, 4 for midsize for Honda. And that those different outcomes, 24 unique outcomes, come out with it. But we could use the fundamental counting principle. And this basically says we multiply the number of outcomes within each component to get the total, rather than developing a decision tree like this. We could see how many possible outcomes are there for car makes, that's 3. How many for car sizes, that's 2. And how many for colors, that's 4. 3 times 2 is 6 times 4 is 24. And you see, much easier and simpler to get this answer by just determining the outcomes and multiplying times the different groupings rather than developing a decision tree. Or I should say a series of decision trees. Now, how many possibilities for a 4-digit number using the digits anywhere from 1 through 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Well, I can use any of them. For the first one, I could have 10 choices. A 1, a 2, or a 3, or a 4, and so on. My second one, I could have 10 possible choices. My third one, 10 possible choices. And my fourth digit, 10 possible choices. Multiply 10 times 10 times 10 times 10. There are 10,000 choices. And if you think about it, if we go from 0000 to 9999, there are actually 10,000 choices. Now, let's change this a little bit. Let's suppose we said you cannot use the same number twice. And I've given an example here. I pulled a number out, but it doesn't matter which number you pull out. You just can't use it twice. So for my first digit, I have 10 choices, anywhere from 1 through 0. But then on my second choice, I can't use all the numbers. Let's suppose I pull a 0 out. Now I've got 9 choices. And then in my third digit, I've only got 8 choices. I can't use the first 2 that I've pulled out, which I pulled out to 0 to 9. Now I'm left to 8. And then on the fourth, I can't use the previous 3. So I've got 7 choices. And if I want to know how many unique numbers there are with no digits repeating, it actually would be 10 times 9 times 8 times 7, which ends up being 5,040. Now we talk about probability, we talk about classical probability. This is where there's an equal possibility of all the events occurring. For example, I've got a 50-50 chance of getting a head, a 50% chance of getting a tail when I flip a coin. There's one possibility of a head, and the total outcomes are a head or a tail. So one event, which is 1, and then there's 2 outcomes, that's 2.5. I can do the same with a die as well. What's the possibility of getting a 1 when I roll a die? Well, there are 6 outcomes, 1, 2, 3, 4, 5, or 6. And what's the possibility of getting a 1? And that's 1 out of 6, which is 1.67. Same for a 2 out of 1 through 6, and that's 1.67. In all, if you notice, with both the coin as well as the die here, if we add up all those possibilities, they add up to 100%. 16.7% plus 16.7% plus 16.7% plus 16.7% plus 16.7% plus 16.7% is 100%. Now we're talking about what's the likelihood of happening. This is where we summarize up the possibility of an event happening. What's the possibility of rolling a die that's a 1 or a 2 or a 3 or a 4? Well, each individual die possibility has a 0.167 or 16.7%. Now, what I'm asking you is, what's the possibility of getting less than 5? Or 1, another way of saying 1 or 2 or 3 or 4. Well, that would be 16.7% plus 16.7% plus 16.7% plus 16.7% or 67%. If you think about this, there's 6 sides in a die. We're looking at the first 4 possibilities, 4 out of 6, 2 out of 3, or 67%. Now, there is also the empirical probability. And this is based on observations. This is more often what occurs in real life is when we have a poll or we're doing a survey. We look at the number of events within each category and then the total events. I've got a little survey here of what people are reading. there are actually 1,490 individuals, and I want to know how many are in different categories. How many read only digital books? 91 of them. How many read both digital and print books? 426 of them. How many don't read any books? 395 of them. How many only read print books? 578. When I add those up, my total number of events, which is 426 plus 395 plus 570 plus 91, is 1490. If I want to know the number of individuals who are only reading print books out of the total, what's the probability? I would say 578 divided by 1490, or 38.8%. Now, if I want to know how this is based for the entire United States, it is almost impossible to survey the 320 million people that live here, right? 330 million people live here. We use this as a sample. We could roughly say out of a sample of 1490, 578 read only print, or 38.8%. And this is where we use probability with statistics as a representation of the whole population. We could look at a frequency table. I look at different age ranges here of just how many people, are within this different age ranges. From age ranges 18 to 22, 156, 23 to 35, 312, 36 to 49, 254. From 50 to 64 is 195, and people who are 65 or greater, 58. When I add all these numbers up, each individual frequency, I get a total frequency of 975. Now, what I want to do here is I want to know what's the probability of someone is above age range 23 to 35. And what I would look at here is 312 divided by 975. There are 312 individuals between 23 and 35 divided by 975, or 32%. So there's a 32% chance when I look at this group that the individual be between the age of 23 and 35. Now, one of the things we look at, and this is where you talk about expertise of individuals, and that can be wide-ranging as well as highly opinionated, is subjective probability. These are based on educated guesses, intuition, prior experience. And I say that because you got people like Steve Jobs who had no prior data to know that if someone would like an iPhone, because there was nothing like that before. So he's using intuition. But we still want to quantify the likelihood of success or failure based on subjective probability. And we use terminologies like impossible, unlikely, even chance, likely, certain. Impossible gives us 0%. Remember, the highest can be 100%. That'd be certain. Even chance, that's 50-50. It's 50% chance. Unlikely, about 25%. Likely, 75%. Again, these are just educated guesses. But if we want to quantify it, we would use these numbers. Now, we can also look at the complement. The complement is what the likelihood of an event not occurring given that event occurs. Now, we call this, if the event is a certain percent, that's the P of E, 32%. The complement is the counter of that. That's called E prime. And if our event is 32%, then the event prime would be 100% the total amount. My 32% is 68%. So when we got 32% before that are aged between 23 and 35, which is a 312, 975, we had 32%. We would say, what is the likelihood of an event of these individuals not being between the ages 23 and 35? That's 68%. That's 100% minus our 32% for that range, which equals 68%.